Okay. All speakers and listeners, welcome to our conference. Together, we will hold the session of the conference on Sunday afternoon in this hall. Firstly, I want to introduce myself. My name is Mehmet Hakan Demir. Uh, I am working at Department of Mechatronics Engineering in Iskenderun Technical University. My study areas are thermoelasticity and machine theory and control theory. Uh, as you know, this is the last session of this whole, and I hope it will uh, go well like previous sessions. We have 10 presentations in this session. Before proceeding with the presentation, I would like to remind you a few important situations. All presentations made in this session will be broadcast live on YouTube, streaming live in YouTube, and will be recorded at the same time. Uh, as you know, some speakers will make their presentations live, and some will make their presentation over videos that have been sent to us before. As speakers you have who have sent their videos can also present live according to their preferences. Before each presentation, I will ask the speakers who are here if they want to present it live or on video with video. Okay, we will start with the first presentation. Paper ID is 38. It's presented by Mr. Yiğit, but he isn't here, I think. Uh, and second one is uh, ID 39, and it is also presented by Mr. Yiğit again. Oh, he isn't here. I think I can't see his name. And okay, we continue with the third presentation. Its ID is 51. It's presented by Murat Atkaya, Mr. Atkaya. Mr. Atkaya, you present it live or in with video?
I would like to present it with video.
Okay. I will run your video. Wait a minute, please. Okay, it's here. Okay. Share screen. I can't see the. Wait a minute, please. Okay. Can you see the video?
Yes.
Okay, I will start.
Hello everyone, this is Murat Atkaya speaking. Today I'm going to make a presentation for my conference paper. My topic is study the effects of electron beam welding process parameters on thick aluminum 6061 T6 condition material. My co-author is Muhammed Abdelmoğla and my professor is Gökhan Küçüktürk, Mr. Gökhan Küçüktürk. Here is my presentation contents. My presentation has 6 sections, which are bio, introduction, model development, numerical solution, result and discussion, and conclusion. Here is my bio. I have graduated from the Eskişehir Osman Gazi University on Mechanical Engineering Department in 2016. I'm still doing my master on GAZİ University in Mechanical Engineering Department. I have been working Turkish aerospace industry since 2019 as a power transmission system design engineer on helicopter group. Here is the introduction. Nowadays, aluminum alloys are used in many fields such as the aircraft, vehicles, and defense industries. Due to its superior mechanical physical and chemical properties, and also due to its ease, manufacture and processing methods. Welding is considered the simplest and the cheapest manufacturing method to produce metallic parts. There are many types of welding, such as fusion welding, solid state welding, diffusion welding, and electron beam welding. Electron beam welding is a welding process that uses electron beam with the high energy density to melt the entire materials and weld them together. Electron beam welding has some advantages over the other welding process, such as deeper penetration can be achieved, high overall energy efficiency, large depth to width ratio, very small heat affected zone, high energy density that can melt the gap between the two materials without distortion, and the ability to apply in a vacuum environment. Previous advances of the electron beam welding have been made to be useful extensively in the aerospace industry for welding of aluminum alloys. Electron beam welding process has many parameters that have to be investigated and optimized for the welded material. These parameters are beam current, beam accelerating voltage, spot size, welding speed, and the beam pattern. Wrong selection of these parameters can make problem in form of defects in the heat affected zone, which could seriously influence the mechanical properties of the welded joint. In this study, the electron beam welding of aluminium 6061 with the T6 condition plate with T6 millimeters thickness was investigated numerically and experimentally. For the numerical study, a 3D computational fluid dynamics model has been developed to study the electron beam welding. The model includes a user-defined function for the electron beam heat sources and the material properties as a function of temperature that have been written and compiled via ANSYS 20 R1 software. The model is validated by comparing the melted zone size obtained numerically and experimentally. Here is the model development section. The heat transfer from the electron beam sources to the specimens is simulated in the developed CFD model by using the heat transfer model in ANSYS Fluent software. In addition, a user-defined function for the electron beam welding, heat source, and the material properties depending on the temperature according to Huan is written and compiled by ANSYS Fluent software. Also, the solidification and the melting are also included to the measure to the achieved melted depth. Heat transfer model. The heat transfer from the electron beam sources to the specimen can be described by the energy equation. The energy equation's parameter depends on the following variables, such as temperature, density, specific heat, thermal conductivity, and electron beam heat sources. Electron beam heat sources depends on beam diameter, beam power, and the voltage. Melting and solidification module. The melting and solidification are taken into account, and the enthalpy technique is used to describe the melting and solidification that occurs during welding process. The enthalpy technique is based mainly on the enthalpy of the material. Here is the equation. H is equal to U plus P times V, or H is equal to minor H plus delta major H, where U is the internal energy, P is the pressure, V is the change in the volume. Then minor H is the sensible heat and the delta H is the latent heat. So the minor H is equal to minor H reference plus Cp times delta T. Delta major H is equal to beta times L. So where minor H references L, Cp and beta are reference enthalpy, the latent heat, specific heat, and the liquid fraction in the material respectively. The liquid fraction beta can be calculated as beta is equal to, open the parenthesis, T minus T solidus, close the parenthesis, over, open the parenthesis, T liquidus minus T solidus, close the parenthesis. By calculating the temperature T through the solution of the energy equation, beta can be calculated. Then beta can be used to define the melting or solidification in the material. Here is the model geometry section. The model used in the analysis is shown in figure 1, figure in below actually, where it is standard tension specimen according to ACTM E8/E8M 16A. As can be seen, the model is sliced the two identical halves to simulate the real processes experimentally. Where in the experimental setup, the specimen is cut to two halves and then welded using the electron beam welding. The dimensions of the model are according to ACTM E8/E8M and 16A. Here is the model I used. And the numerical solution. The equations that are described on the previous slides include the heat transfer, solidification, and melting equations are solved using by ANSYS Fluent 20R1 software. Also, a user-defined function code that contains the electron beam welding parameters such as electron beam diameter and welding speed is compiled and solved. To validate model, the obtained results from the model are compared with the experimental results. So here you can see our calculated width, welding width is around 3.48 and the real one is 4.46. So by comparing the dimensions of the melted zone in the both experimental and the numerical results, it can be found that the maximum obtained error is around 11.7%. That can be acceptable. Therefore, the numerical model can be used for the initial investigation of the welding parameters effect. So, result and discussion. The numerical results from the computational fluid dynamics model can be used as a guide through the experimental work. The value of the current, voltage, and the welding speed are investigated through the model to make sure that they can melt the whole thickness of the specimen. So, figure 4 shows that the results from the CFD model where both the voltage and the welding speeds are fixed at 60 volt and 30 millimeters per second respectively, and the current is changed. Using 30 milliampere current, electron beam cannot melt the whole thickness as shown in figure 4. By increasing the current to 35 milliampere, the electron beam just can penetrate the specimen thicknesses. So, using 40 milliampere, the current can melt the whole thicknesses, but the melt width at the bottom of the specimen is narrow, and this can affect welding quality. So, increasing the current 42 or 44 milliampere led to increasing the melted thickness at the bottom of the specimen, as can be seen, but may affect the surface quality at the bottom of the specimen. It can be concluded that using current value 40 milliampere and above is recommended for the specimen, and by carrying out the experimental test, it can be accurately determine the best current value. So, for the experimental study, a 6 mm thick aluminum 6061 T6 condition aluminum alloy was used to prepare the welding specimen in the form of tensile test according to ACTM E8/E8M 16A. No defects in the welding path can be seen for the tested specimen as shown in the figure 6. Using 40 milliampere, very small defects can be seen on the bottom surface. Increasing the current over 40 milliampere, the defects are increasing also. So here you can see the results of the experimental value. Therefore, it can be included that optimal parameters for the specimens are 40 mA, 60 volt, and 30 mm per second based on the visual inspection on the top and bottom surface. More analysis is required to fully optimize the parameters for aluminum 6061 T6 condition based on the micro hardness and tension test, which is going to be investigated in another study. In conclusion, in this study, the electron beam welding of aluminum 6061 T6 condition is investigated numerically and experimentally. A CFT model is developed to simulate the EBW process through a user-defined function that written, compiled, and solved using by ANSYS Fluent 20R1. The results from the CFT model is validated experimentally by comparing the melted zone numerically and experimentally. Then the results from the model was used as a guide through the experimental work. The main results of this study is summarized as follows. According to the CFT model, using 60 volt, 30 mm per second and beam current more than 35 mA can melt the specimen thicknesses. From the experimental work, using 60 volt, 30 mm per second and the beam current more than 40 mA can cause defects on the bottom of the specimen. Therefore, the optimal parameters of electron beam welding of aluminum 6061 T6 condition 6 mm in thickness are 60 volt, 30 mm per second and 40 mA to obtain a good surface quality. For fully optimize the process parameters of the electron beam welding for aluminum, other criteria need to be investigated, such as micro hardness and tension test, which is going to be studied in another study. And the SEM analysis for the welding areas shows that the narrow heat affected zone after electron beam welding process is obtained. No obvious boundaries can be seen between the base material and the heat affected zone. In acknowledgement section, I would like to thanks for the Turkish aerospace industry for technical and financial support. Here is my references. You can see I also put this on paper. So this is my presentation. So if you have any question, please let me know. I will try to answer you. Thank you.
Mr. Atkaya, thank you for your very nice presentation. Is there any question or suggestion? I think no. Thank you again. And we will continue with the following presentation. I think I checked the participant and Mr. Yiğit is not here now. We go to the we will continue the following presentation. Its ID is 106. It's presented by Talha Ersöz. Mr. Ersöz is not here again, and I checked he sent their video, and I will run this video now. Okay.
Hello everyone, my name is Talha Ersöz and today I'm going to present you the study named as an experimental investigation of hardness and microstructure of 2024 aluminum alloy by equal channel angular pressing combined with heat treatment. This is my outline. First we'll go through the introduction, then material and method, then results and discussion, and then conclusion. First of all, how to obtain the ultrafine grains. We have 4 different techniques. The first one is vapor deposition. Second one is high energy ball milling. Third one is fast solidification, and the final one, which we are interested in, is cerebroplastic deformation. And what is SPD? SPD is a method of processing metals to create bulk material comprised of nanostructures. So basically, we get coarse grains into smaller grains as a result of the SPD. As the finer the grains, we get higher strength, and as a result of this, we get the fracture toughness. So the ultra-fine grains were obtained by using equal channel angular pressing technique, which is a cerebroplastic deformation method. As the grains get finer, the mechanical properties of the material increase significantly according to the hole and patch location, as shown on the screen. In this present study, 2024 quality aluminum alloy was subjected to ECAP with 1, 2, 3, and 4 pass cycles after solution heat treatment, and then these samples were aged at 175 centigrade degrees for 8 hours. After the aging, the hardness values and optical microstructures of the samples have been investigated. The hardness of the material decreases when 2024 quality aluminum was pressed with ECAP and then aged. The hardness decrease ratio after the aging was found to be directly proportional to the sample's number of pass through the ECAP. So let me just explain you the ECAP die briefly. So we have a billet is pressed through a die consisting of two channels with identical cross sections intersecting at an angle of between 60 to 135 degrees, and we have a rounded or zero corner. And this is the basic strain formula with the angles, and with the 0 and 90 degree values we get the strain of 1.155, and with ECAP we can get 300 and 500 nanometer grain sizes. So for the material and method section, we have used in this study 2024 aluminum alloy. The composition is shown on the table, and the aim of this study is to investigate the hardness and microstructural properties of 2024 aluminum post ECAP aging at 175 degrees for 8 hours. And the ECAP die that process is carried out at room temperature with 1 pass, 2 passes, 3 passes, and 4 passes, with an ECAP die having an angle of 135 degrees. The ECAP die's technical drawing is shown on the screen. These are the exact dimensions. So on the left side we can see I have made an modification after the you can see the images on the left side, the photos of the die. The technical drawing is a little bit different of this photo, so I will explain why I have changed the ECAP die's dimensions. And on the right side we can see the simulations. As a result of the simulations, as you can see, there is a difference between this photo and this simulation. I will explain you right now. But first of all, the surface quality is very important for ECAP. Therefore, the surface where the material is going to be touched is carefully polished before the operation, as indicated on the top left photo. It's like a mirror image. ECAP die is subjected to heat treatment to obtain required hardness. Another important point for the ECAP die is the friction of the surface. In order to minimize the friction, we have applied nitration heat treatment. The surface hardness is obtained with 62 HRC. After all these works are finished, the die is assembled carefully. The outer shell is also assembled in the die to prevent it opening during the operation. The channel has a cross-section with the lengths of 90 mm for each side of the channel. Hence, the samples are machined to 18.95 mm in the cross-sectional dimension and 40 mm in longitudinal dimension. Then the ECAP die is assembled as shown. We have assembled this ECAP die into this outer shell. The samples are solutionized at 525 centigrade degrees for 2 hours before ECAP. After solutionizing, the samples are pressed at 12 mm per second and at room temperature. We have selected graphite powder in spherical shape as a lubricating agent instead of molybdenum disulfide, because molybdenum disulfide has a rectangular shape. At first trials, the samples pass through the turn at the ECAP die, but after that, the samples expand and fit to the channel. Two male punches were plastically deformed, however, the samples inside the channels do not even move a bit. Then, the ECAP die set is assembled from the outer shell, and the samples stick inside the channels as shown on the middle picture photo. The billets are stick inside. It's not possible to take them out. So during the cleaning of the samples stick inside the channels, too much force is needed to be applied for the samples passed through the turn. So it was nearly impossible to take these two billets out. And in order to solve this problem, the channel is expanded 1 millimeter after the curvature of the turn is completed. As you can see on this simulation figure, also on this technical drawing, the channel is expanded a little bit. And then the sticking of the samples inside the ECAP die is solved. Finally, the ECAP die works smoothly. 1 pass, 2 passes, 3 passes, and 4 passes have been made with the ECAP die. The optimum aging duration is found out with the aging the solutionized samples at 175 degrees for 4, 6, 8, 10, and 12 hours. The optimum duration is found as 8 hours at 175 degrees. Then the aging operation is carried out with the parts. The samples are put in an electrically heated laboratory type furnace and aging is carried out at 175 degrees for 8 hours. After the aging, the microstructures and the hardness values are investigated. First of all, let us see the microstructures. And on the left side, which is indicated as A, the sample is in extruded condition. It can be seen from the elongated grains on the figure. The size of the elongated grains is around 100 microns for the solutionized sample. And on the middle one which is indicated with B, the one-pass ECAP samples microstructure is shown. The shear bands on the grains can be clearly observed and the grain size is around 50 microns. So the grains are becoming almost half with only one ECAP pass. So on the right side, which is indicated as C, this is a microstructure of the 4 passes ECAP sample. So the shear bands are observed more homogeneously distributed along the microstructure. In this case, the grains get almost 4 times smaller with 12 microns grain sizes. So, and for the graphics of the hardness and number of passes and the hardness and the aging duration, the hardness values are increased directly proportional to the ECAP pass number. So on the right side, right graphic, we can see the hardness increasing with increase of the number of passes. So after the aging operation, the hardness values of the samples which is not ECAPed is increased. The hardness values of the samples which are passed through ECAP are decreased. So we have applied ECAP and measured the hardness values, and then we have put all these one pass, 2 passes, 3 passes, and 4 passes samples to the aging operation, and as a result of the aging, the hardness of the samples are decreased as indicated on the graphic. The higher the number of passes, the higher the decrease at the hardness value. The hardness values of samples as solutionized are 132 hardness Vickers 5, and the hardness values of the samples which are not ECAPed but aged at 175 centigrade degrees for 4, 6, 8, 10, and 12 hours are given on the left graphic, and the hardness values of the samples after ECAP plus aging are given on the right figure. Okay, so as we can see, the decrease in the hardness for 1 pass is on a 5. For 4 pass, it is 15. So let us pass through the conclusion. In the conclusion, the ECAP is one of the essential methods for SPD applications. By applying ECAP, the grain refinement is obtained by the formation of new high-angle grain boundaries. In addition, the high-angle grain boundaries, high dislocation density is obtained with ECAP. Therefore, the hardness of the samples passed through ECAP increases as the number of passes increases. The further the ECAP repetition, the higher the possibility of ultrafine grain obtainment. The ECAP die design is very critical in order to make the experiment without any problems. The angles at the curvature, the heat treatment, lubricant, and the equipment are the key factors to successfully perform the ECAP process. Aging after ECAP decreases the hardness due to the nucleations on the segregated atoms located at the dislocation zones. High dislocations could cause overaged conditions to the material, and high dislocation density will increase the probability of dislocation and annihilation due to the short distances between dislocations. By using SPD methods, especially ECAP, very significant grain refinement and the potential for producing advanced engineering materials having superior properties, which are strength, ductility, and good fatigue characteristics, can be achieved. And these UFG structures lead to an increase in strength, but they may also lead to a weakening if the processing conditions introduce significant changes in the precipitate morphology. If the UFGs are reasonably stable at elevated temperatures, there's a potential for achieving excellent superplastic properties. So that's all from my presentation. Thank you for your kind attention. If you have any questions, please do not hesitate to ask me. Thank you very much again.
Okay, thank you, Mr. Ersoy. I think he didn't attend. He don't attend this session, and he's not here. If you want ask a question, I think you mailed him. Now we are continuing with the other presentation. His ID is 115 and its name structural optimization of airplane component using topology optimization for additive manufacturing. Is presented by Ms. Aslan. Are you here? Okay.
Yes, I'm here.
Okay. You present live or I will run the video?
I will present it with video. Yes.
Okay, okay. I will run your video. ID 1. Okay. Okay. I can see your video. Sorry. Okay. Yes, it started now.
Hi everyone. Firstly, I want to talk about myself. My name is Büşra Aslan. I am a doctor of philosophy in mechanical engineering, and I am working as a research assistant at GAZİ University. First of all, I would like to thank my advisor, Professor Dr. Oğuzhan Yılmaz, for their helping me. And then I can start my presentation. The name of our study, Structural Optimization of Airplane Component using Topology Optimization for Additive Manufacturing. Firstly, I want to tell what is the additive manufacturing. Additive manufacturing is the process of taking the data of the design from the digital and producing it by adding layer by layer. And the most important advantage provided by the designer can freely develop a model without question it is manufacturability. Additive manufacturing process flow this type: 1. CAD 3D model, 2. STL file creation, 3. sliced layers, 4. printing, 5. post-printing processing. Structural optimization. Structural optimization can be defined as the process of choosing the best variable from among applicable solutions. It can be used for weight reduction, maximum rigidity, natural frequency reduction, and maximizing heat conduction. Topology optimization, size optimization, and shape optimization are generally used as structural optimization methods. we was used topology optimization in our study. Topology optimization is used to find the best material distribution on the model and to reach optimum weight by removing materials from unnecessary area. We must choose a bearing bracket of aircraft for topology optimization. The bearing bracket is a common component in the control surfaces of various aircraft, and then the bracket redesigning for additive manufacturing can significantly save weight and help reduce aircraft fuel consumption. Firstly, we prepared CAT model and we applied mesh structure. Then we divided the model as design and non-design area. Design area was showed with dark blue and non-design area was showed with light blue. After this is finished, other parameters that should be used during optimization are determined. This parameter may be, I can say, forces and boundary condition, constraints, objective function, etc. The desired regions were fixed with one-dimensional rigid elements, and we applied 3 loads in X, Y, Z direction. We used OptiStrack module of HyperMesh for topology optimization and static analysis. After topology optimization, HyperMesh gave us this design. And then we prepared our own design by taking this model as an example. After that, we used NetFab in our study. NetFab provides a complete workflow from start to finish, and this provides a fast and easy method. Using NetFab simulation, support materials was defined and production analysis was made. Here, we have shown our analysis results of both the existing model and the new R design. The maximum stress results, it was observed that the stress value increased after topology optimization. But this result is below yield stress and can be neglected. And I can say 30% reduction in weight. And according to NetFab simulation results, the model was found to be proceedable. In this study, the aim was to show the effect of topology optimization on weight, displacement, and stress, with the analysis carried out and the data obtained. It was observed that 30% reduction in weight. Later, we applied cost analysis. We saw 69% reduction. Finally, when we look at production time, it was seen that there is a decrease of approximately 25%. Thank you. My presentation is finished.
Thank you, Ms. Aslan, for your presentation. Is there any question?
Yes, I have some question to ask.
Okay.
Okay. First, I am asking about for the model, for the force. You applied the concentrated force at the whole in the model.
I can't hear you.
Can you hear me now?
Now here.
Yes, yes. In your model, you applied concentrated force at the hole.
Yes, as the whole.
Yeah.
Actually, sorry.
Because
Uh-huh.
this load is a bearing load. It is not concentrated load. I think it is better to apply a bearing load, not concentrated load.
Yes, thank you. We use we show that topology optimization effect on the model, and then we aim to affected topology optimization.
Okay.
Yeah.
Also, there is another question. When you make topology optimization, I saw that the displacement is increased.
Yes, but yield strength is fall. Yes, less than increase, but yield strength more. Sorry.
Yes, but you have to focus because bracket, you have to focus on rigidity because the rigidity is very important. You have to focus on the displacement more than the stress in this case of design, because the bracket carry a beam or carry something like that, so you don't need it to move, or displacement 1 millimeter. So after the topology optimization, the displacement increased. So it is very important to consider displacement than stress in this case of topology optimization.
Yes, it is true. And maybe if you want, let's talk by email with you.
Yes, sure. Yes. Thank you very much for your presentation. Yes.
Thank you.
Okay, thank you, Mr. Abdelmullah, for your questions and comments. Okay, is there any question? More? I think no. I will check the YouTube channel. There is no question or any suggestion. Okay. Thank you for your presentation again, Ms. Aslan, and we continue with the other presentations. The following one is investigation of laser polishing on the surface of the parts produced by additive manufacturing. It's presented by Mr. Nestle. Mr. Nestle, are you here?
Hello,
Hello.
I'm here, yes.
Okay.
I actually can start the video. I think, okay, yes, I'm here.
Okay, you prepare video?
Yes, I prefer this video. Please.
Okay, I will start.
Okay.
I'm sorry. Yes, so video.
Hello everyone, my name is Shafak.
Sorry. I'm not good at this. Okay. Close. Okay.
Hello everyone, my name is Shafak Nesli and I am a PhD candidate in the Department of Mechanical Engineering in GAZİ University. My advisor is Professor Dr. Oğuzhan Yılmaz and our research is investigation of laser polishing on the surface of the parts which are produced by additive manufacturing. Additive manufacturing is an advanced manufacturing method that builds the parts in a layering manner by reshaping the source material. Nowadays, additive manufacturing is not only a prototyping technology, but also a production method, especially for the complex shaped parts that cannot be produced with traditional manufacturing methods. Due to these advantages, it has become a preferred method, especially in the fields of aerospace industries, architectural, dental, automotive, furniture, and biomedical. When we see this figure, we have a topology optimization and the bracket transforms from this shape to this shape. And when we see this figure, buildings can actually be produced very differently. And of course, we could have inspiring approach to the medical industry with additive manufacturing. And it is very inspiring actually. And also, automotive components could be redesigned with respect of the additive manufacturing. However, these parts cannot be directly used in the industry without post-processing. The high surface roughness of value of these parts is one of the reasons for this situation. As you see here, there are two samples which are produced by two different additive manufacturing techniques. The material of the first part is Inconel 265 and it is produced with SLM technology, which is selective laser melting, and the material of the second part is a titanium alloy and it is produced with electron beam melting technology. As you see, the surface of these parts are very rough and these parts cannot be accepted in the industry without post-processing. Uncontrolled surface roughness could significantly affect the fatigue life and the crack initiation. So, laser polishing is an innovative part finishing technique that can be used to reduce the surface roughness by melting a thin layer of material on the part surface. Laser polishing involves melting a thin layer of the substrate with surface tension, causing the material to flow from peak to volleys. In laser polishing, the material is not removed, but is relocated as a molten pool. As you see in the figures, laser head moves from one side to other. With the movement of the laser head, a thin layer of the surface melts, and then, with the effect of the surface tension and the gravity, melted materials move into the pits. In this way, more smooth surfaces could be achieved. In this work, the part was produced by the SLM method that used 10 to 40 micrometer Inconel 2625 super alloy powder. The dimensions of the rectangular prism-shaped part were 80, 11, 11 micrometers. The table shows the parameters of SLM. Laser power was selected as 285 watts. Laser scan speed was 960 millimeters per second and the powder particle size 10 to 40 micrometers. And as the actual laser polishing was applied on this surface. Laser polishing was processed on the surface of the SLM Inconel 625 part using the laser parameters given in the table. The laser power was selected as 600 watts. Laser scan speed was 200 millimeters per second. Hedge distance, which can be defined as the distance between two laser tracks, that was 0.03 millimeters. Pulse frequency was 1000 Hz and pulse duration was 0.0008 seconds. The process was covered under argon gas because oxidation was a problem in this process, and the surface roughness before and after laser polishing was measured and inspected in order to assess the changes induced by laser polishing. In this work, a new polishing method, laser polishing, was applied onto the surface of additive manufacturing Inconel 625 part. Surface roughness values can be numerically defined with the roughness parameters such as roughness average RA, root mean square roughness RQ, the average of the height difference between the 5 highest peaks and the 5 lowest valleys RZ. As can be seen in the figures, the surface roughness has decreased significantly. The right side of the figures represent the as-built surface, while the left side represents the laser polished surface. Roughness values of as-built surface RA, RQ, and RZ was 10.91 micrometers, 14.82 micrometers, and 64.57 micrometers respectively. And when we check the laser polished surface, RA, RQ, and RZ was 2.34 micrometers, 2.84 micrometers, and 10.76 micrometers respectively. And actually, besides, we can observe the layer thickness of the parts from the as-built surface and laser hedge distance, which I said before, it is the distance between two laser tracks, can be observed from the laser polished surface in the figures. As a conclusion, with the additive manufacturing method, it is expected that complex parts will take place more frequently in the industry. The laser polishing, which emerged as an alternative method to traditional methods, can be used to reduce the roughness of the surface, especially complex parts. It was observed that with the application of laser polishing onto the surface of the part produced with SLM, the surface roughness was successfully improved and RA values decreased from 10.91 micrometers to 2.34 micrometers. In this work, 78.4% roughness reduction was successfully achieved in the surface roughness by applying laser polishing. Thank you for listening to me, and if you have any questions, I will be happy to answer them now. Thank you.
Thank you, Mr. Nestle,
Thank
for your
you.
presentation. Is there any question or suggestion? Okay, there's no question. Thank you again, Mr. Nestle.
Thank you.
And we continue with other presentation. The following one is simulation of multi-layer selective laser sintering of silicon carbide. It's presented by Mr. Afternon. Mr. Afternon is here, I think. Can you hear me, Mr. Afternon?
Yes, I'm here. Yes, I'm here.
Okay, I think you present live.
Yes.
And you can please you can share your screen and presentation, your slides. We are waiting. Oh. Yes, we see your presentation now.
Okay.
Okay. If you want, if you're ready, you can start.
Okay. Hello everyone, my name is Mohammed Abdelmoula and I am a PhD student at GAZİ University Mechanical Engineering Department. And I am also working as a listing researcher at the DOCA 3D printing project. My study is under supervision of Professor Gökhan Koçukturk. And today I'm going to talk about our paper. It is about simulation of multi-layering selective laser sintering of silicon carbide. The content of my presentation, first I will talk about the project development of ceramics printing project, and then I will talk about the paper simulation of multi-layering selective laser sintering of silicon carbide. For the paper, I will talk about the model that we develop and the validation of this model and result discussion and the conclusion from this study. For the development of ceramic 3D printing project, it is a project that is funded from EU, and it has contained 6 academic and 1 non-profit association and 7 industrial companies. The project is mainly focusing on 3D printing and the manufacturing of ceramic material, and there are 14 students working in this project. 2 of them here in Turkey, one in GAZİ University, me, and there is another student in Ermeksan company in Bursa. For our paper, we develop a CFD models that can simulate the multi-layering SLM and SLS for ceramic material. The model work as follows. First, the laser scan a layer, and after finishing the first layer, there is another layer that is deposited on the first layer, and the laser scan the layer. And by this way, until finishing the whole part. The development code has some feature like first, the deposition time is taken into consideration, and also the inlet gas properties are included. Also, you can select scanning strategy to be applied to the layer, and you can obtain the temperature history during the scanning process from this model also. Finally, you can calculate the thermal stress and distortion of the model of the part you produce it. For the model validation, we validated our model with the data available in literature, where we validated with the work of Sang, and we found that there is a very close identity between the 2 results, and the maximum error was 3.35%. Also, we made another validation with another study where we compared the contour from the model, the laser spot diameter contour from the model with the contour from thermal camera, and we found that there is very close identity between the 2 results, as you can see. For the result and discussion, first we studied the laser power and the scanning speed that can be used in SLS of silicon carbide, where we used a range of laser power and the scanning speed according to the printer manufactured by 3D System company, where the laser type used in this printer is fiber laser, and the laser power range up to 300 watt, scanning speed up to 1000 millimeter per second. Laser spot diameter 70 micrometer, and the layer thickness used in the model 50 micrometer, and the hatching distance is 35 micrometer. And we run the model, and we obtain this figure, where this figure you can see that there is different power used with different scanning strategy, and we obtain the range for the laser power and the scanning speeds that can be used in SLS without any problems. You can see here this line is the centering limit, and the above line or red line, the red dash line is the decomposition limit. So all the values that lie between these 2 limits can be used in SLS of silicon carbide. The values above the decomposition limit cannot be used because decomposition will happen if we use. And also the values below the centering limit cannot be used because centering will not happen for silicon carbide if we used. So we can only use the values inside this area. So in our study, we use this value where we use like laser power of 50 watt and scanning speed of 1000 millimeter per second. After that, we studied the effect of the scanning strategy and build orientation, where we used this scanning strategy and build orientation in our study using 50 watt. for laser power and 1000 millimeter per second for scanning speed. And we obtain the temperature history during the whole process of the building, where you can see that the green line present the temperature history for the scanning process, the whole scanning process. And each line of this green line, if we expand, we will obtain the scanning history for one layer. So our part, we have 10 layers in our part. So if we expand this line, we can obtain the scanning for one layer. And we can see that by increasing the layers, we can see that the scanning temperature exceeds the recommended limit by this way. And this is mainly due to the heat accumulation inside the silicon carbide, because silicon carbide thermal conductivity is very, very low. And due to the heat accumulation inside the part, the temperature of the part increased, leading to exceed the recomposition limit in the upper layers. And if we see the temperature history for the layer number 9, we can see that all the scanning is above the recomposition limit, and this is the problem. So how to solve this problem? This problem can be solved by controlling the temperature or controlling the scanning speed. The temperature can be controlled either using a controller for the power, where we can reduce the power according to the number of layers. So we updated our model and we included a subroutine for laser power controller in the building, during building. And when we applied this subroutine, we can see that the scanning is below the recomposition limit for the layer number 9. And also we obtained the variation of the laser power with time during the scanning of the layer number 9. We can see that the subroutine makes the power start with 49. Although we used 50 watt in the model, but the subroutine reduces the power to 49 because of the heat accumulated inside the part. And during the scanning, it is reduced by this line until it is like 48.1 watt. For thermal stress and deformation contour, we obtained from the model the temperature distribution for the printed part. And we studied the thermal stress and deformation at 1500 Kelvin. And when we calculated the thermal stress, we found that the stress is high the yield limit. But here you can see that this figure is a yield limit, and you cannot use this figure to determine if there is a problem happened in the part, or there is a cracks or something like that. So we normalize this stress. Normalization means that we divided this stress by the yield stress. As you can see here, this is the normalized stress. The stress above 1 means that the yield happened. So that means that there is a cracks, there is a defect in the part, and any values below 1, no problem. So in this part we exceeded 1, so we have cracks in this part and we have defects will happen during printing. So how to solve this problem? It can be solved using preheating. When we preheating the part during printing using 500 Kelvin, we can see that the thermal stress reduced to 0.86. So preheating is very, very important for SLS and SLM of ceramic material. And also the distortion also decreased. If you can see, the distortion before preheating was 0.06, but after we applied the preheating in the model, the distortion reduced to 0.14. So the conclusion of this study, first, the model or the development model that we used can provide us with the temperature history, and can provide us with the temperature distribution and we can use this temperature distribution for the calculation of the thermal stress and also the calculation of the distortion inside the part. Also for ceramic material, it is important to apply temperature controller during the printing process, because due to the thermal conductivity of the low thermal conductivity of ceramic material makes the heat accumulated inside the part, and during the printing the heat will exceed the recomposition limit. So it is important to consider the controller for the laser power. And also it is important to include the preheating for the chamber, because ceramic material, the centering point for ceramic material or the melting point for ceramic material is very high, more than 2000 Celsius. So to reach the temperature from like room temperature to 2000, it is very high temperature and cracks will be developed. So we need to reduce this difference by preheating. So it is important to apply preheating for ceramic material. This is my reference I used in the analysis. This is our partner in the project, and thank you very much for your listening. And if you have any question, I will be happy. Thank you.
Thank you, Mr. Abdelmola, for your presentation, and congratulate you and your advisor, Dr. Küçüktürk, for this wonderful study. Is there any question? Thank you, Dr. Küçüktürk.
Thank you very much.
Yeah, we have no question. Okay, thank you again for this study to you, and we will continue Mr. Kurt's presentation. Mr. Abdelmola, please stop the sharing your screen. Thank you. Mr. Kurt is not here, I think. Okay, I checked the video and he didn't send video, and we continue with the following presentation is presented by Volkan Kılıçlı. He said that he will not attend this video, this session, and he sent their video. I will start his video. Okay, I find it, and I will start it. Okay, sorry. Okay, share. Okay.
In this session, I'm going to present my study, which entitled Effect of Stamping Time on Microstructure and Mechanical Properties of Stamped Ductile Iron with Dual-Metric Structures. This study is experimental study currently under investigation my master students Ahmet Uyar. Here you are seeing my presentation sequence: first introduction, second aim and scope, third experimental studies, fourth experimental results, 5 concluding remarks, and final references. Dual-metric structure stamped ductile irons are relatively new type of stamped ductile iron groups with a good combination of strength and ductility. Dual-metric structure stamped ductile iron is produced by intercritical austenitizing plus stamping heat treatment, and they contain ferrite plus spherite structure in their microstructure. Dual-metric structure stamped ductile iron can be produced at different volume fraction of spherite by controlling intercritical austenitizing temperatures. The spherite has been defined as a mixture of bendic ferrite and high carbon stabilized austenite in the stamped ductile irons. You are seeing the typical dual-metric structure stamped ductile iron micrographs in the figure 1. The brown color is spherite and the white color is ferrite, and the black globes is the graphite. The motivation of our study, authors have been investigated the effect of intercritical stenting temperatures and stempering temperatures on the microstructure and mechanical properties of dual metric structures tempered ductile iron. Limited study has been investigated to limited study has been made to investigate the effect of stempering times on the microstructure and mechanical properties of dual metric structure tempered ductile iron so far. In the present study, the effect of stempering time on microstructure and mechanical properties of alloyed tempered ductile iron stenized from intercritical stenting temperatures has been investigated. Experimental studies. The chemical composition of cast alloyed ductile iron used in the present study given in Table 1. The important alloying element is carbon, silicon, manganese, and nickel, molybdenum, and copper. In the present study, we have used alloyed ductile iron in our experimental works. The ductile iron was produced in a medium frequency induction furnace in a commercial foundry. The Tandish-Kaur ladle method was used to treat a 500 kg melt of iron with 6-7% magnesium containing ferrosilicon at 1450 Celsius. Final alkylation was carried out with a 75% ferrosilicon alloy. The melt at the temperature between 1400 and 1450 Celsius was cast into Weiblocks and mold, which were prepared in accordance with ISO 1083 standards. The tensile samples were measured from the Weiblocks bar turning. You are seeing the tensile samples position in the Weiblocks. The tensile samples were intercritically stenized at 800 Celsius for 30 minutes and then rapidly transformed to a salt bed containing 50% sodium nitrate plus 50% sodium nitrate. Salt bed is isothermally held at 350 Celsius for 45 minutes, 60 minutes, 90 minutes, 120 minutes and 180 minutes. Here you are seeing the schematical representation of the box furnace. If we are used for intercritical stenting, we had rapidly transferred the tensile samples in a salt bed. You are seeing schematical representation. Materials characterization samples were cut from the undeformed zone of tensile bars and hot mounted for mechanical grinding and polishing with up to 0.5 micron colloidal silica suspension, and finally samples etched with 2% nitrile solution. We have used Leica DMI 5000M optical microscope for microstructural observation. The volume fraction of spherite and proeutectoid ferrite was calculated by using Leica application suite image analysis software version 5.2. Tensile test was performed to determine the mechanical properties of samples. Tensile tests were carried out at room temperature using an Instron 3269 universal testing machine with 50 kN loading capacity at strain rate of 0.0068 seconds. An extensometer set to a gauge length of 25 mm was used for strain measurement. At least 3 tensile samples were tested for each heat treatment condition, and average values are reported in the paper. The optical microstructures of duometric structure alloy according to stempering times provided in Fig 1. Fig A is 45 minutes, Fig B is 60 minutes, Fig C is 90 minutes, Fig D is 120 minutes, and Fig E is 180 minutes. dual matrix structures clearly observed in all Öz tempering times. No significant change observed in the Öz-ferrite volume fraction. The Öz-tempered volume fraction is constant, 50 or 20% in all Öz-tempering times. But the Öz-ferritic structure became more considerably clear with the increased Öz-tempering time. Moreover, no significant effect has been observed on the morphology of Öz-ferrite depending on the Öz-tempering times. Mechanical properties. The mechanical properties of dual metric structure Öz-tempered ductile iron samples are given in Table 2. As can be seen from the table, both yields and tensile strength increased with increased Öz-tempering times. But after the 120 minutes Öz-tempering time, the tensile strength of the samples decreased. This can be attributed that the similar Öz-tempering kinetics of conventional Öz-tempered ductile iron. The best tensile properties have been obtained at certain Öz-tempering times, called processing window in Öz-tempered ductile irons. Short and long Öz-tempering times can cause deteriorated mechanical properties in Öz-tempered ductile iron. Similarly, after the 120 minutes Öz-tempering time, the tensile properties of samples decreased in dual metric structure Öz-tempered ductile iron. The reduction of tensile properties after 120 minutes attributed the decomposition of high carbon austenite, decomposing the painted ferrite and carbides during the further Öz-tempering times. And final conclusion, the pyrrhotectoid ferrite plus Öz-ferrite microstructure can be produced in an alloyed ductile iron by intercritical austenitizing and Öz-tempering heat treatment process. The optimum combination of strength and ductility can be obtained by changing Öz-tempering times at constant Öz-ferrite volume fraction in dual metric structure Öz-tempered ductile iron. Tensile properties increased with increased Öz-tempering times, but after the 120 minutes Öz-tempering time, the tensile properties decreased. Dual metric structure Öz-tempered ductile iron samples have shown similar Öz-tempering kinetics with conventional Öz-tempered ductile iron. It has been determined from the tensile properties. The best mechanical properties has been obtained in 120 minutes Öz-tempering times in the study. Here you are seeing my references. Thank you for your attention. Have a good conference.
Thank you, Mr. Kılıçlı. Is there any question? Mr. Kılıçlı is not here. You communicate him with mail, I think, if you have a question. Now we are continue with the last presentation of this session. Its name is Etimaden Design, the Future of Boron. It's presented by Miss Maraşlıoğlu. They sent us a video. I will start their video now. Okay.
Hi to everybody. My name is Lütfü Tozar. I am the plant manager of Beylikova Florida Maritime Rare Earth Works of Etimaden. Today, I will present a presentation about Etimaden and boron sector. Hi to everybody. My name is Lütfü Tozar. I am the plant manager of Beylikova Florida. Here's the history of the Etimaden. By the directive of Mustafa Kemal Atatürk, five-sidedness that gives direction to the future, Etimaden was founded in 1935. for the industrial region of Turkey to carry out natural resource and financial organization together with the restructuring in 1998. It was named Eti Holding AG, and in 2004 it was named Eti Maden İşletmeleri Genel Müdürlüğü. Now Eti Maden is the leader of the world boron industry, presenting the boron products obtained from boron and boron products with global logistic operations to the national and international market. Now, Eti Maden, which designs the future of boron, continues its activity with the vision of quality and sustainability. Here is the some milestone for the Eti Maden. As I said before, Eti Bank was established in 1935. Kütahya Cement Plant was established in 1958. Balıkesir Bandırma Borax Plant was established in 1964. Eskişehir Kırka Borax Plant was established in 1970, and the Balıkesir Bugadiç Boron Plant established in 1976, and Bursa Kesterek Clement Plant was established in 1979, and AB Eti Products Oil was established in Finland in 1982, and in 1998, its name changed to Eti Holding AŞ, and from 2004 until present, it is Eti Maden İşletmeleri Genel Müdürlüğü. Sorry for the inconvenience. And these are the some figures about the world boron sector and Eti Maden. Estimated world boron reserves is about 4.5 billion tons, and Eti Maden has a share of 73%. World boron production capacity is about 5.6 million tons, and Eti Maden has a 48% share. World boron market value is about 1.44 billion US dollar, and Eti Maden has a share of 57%, and world boron consumption is about 3.7 million tons. And these are the boron production centers for Eti Maden. Bandırma Boron and Acid Works located in Balıkesir, Bandırma. Emet Boron Works is located in Kütahya, Emet. Bigadiç Boron Works is located in Balıkesir, Bigadiç. And Kırka Boron Works is located in Eskişehir. And Beylikova Florit Baritan Rare Earth Elements Works is a new working area for Eti Maden, is located in Beylikova, Eskişehir, and the General Directorate of Eti Maden is located in Ankara, the capital of Turkey. And Eti Maden has 33 facilities and 4 boron works, as I said before, Bandırma, Bigadiç, Kırka, and Emet. In this work, we are producing 22 boron products, and these are ground colomanite, ground ulexite, concentrated colomanite, concentrated ulexite, granular colomanite, granular ulexite, borax decahydrite, boric acid, etitot 67, calcined tincal, sodium perborate, etibor 48, etibor 68, boron cleaning products, ethical ceramic, boron oxide, zinc borate, Eti-K boron, Eti-K dot, Apple 3367, Borel, and Ethical 43. Eti Maden can produce all boron products used in industrial areas. These are the products and usage area starting from boron ore, going to advanced technology of boron. And from boron ore, colemanite, tincal, and ulexite, and Turkey is the major source of colemanite and tincal. Concentrated boron products used in glass, ceramics, agriculture, iron and steel industry, and in cleaning. And the concentrated colemanite and concentrated ulexite used in these productions. Refined boron products again used in glass, ceramics, agriculture, energy, and flame retardants. And in this area, etibor 48, boric acid, anhydrous borax, etitot 67, and zinc product used. Also in advanced technologies like nuclear industry, electric, electronic, boron fiber, defense industry, and magnets, boron carbide, boron nitride, ferroboron, and elemental boron, and also boron hydride is used. And the next slide will come. And these are the percentage of the boron products as usage area. 48% of boron used in glass production, and 15% used in agriculture as a fertilizer and insecticide, 15% used as ceramic, 3% in detergent, and 19% in other industries. And boron products mainly used in glass, ceramics, and agriculture sectors is not the main component, and it is included as an additive in the final product, and at rates ranging from 0.01 to 25%. As an example, in glass, it's used from 5 to 15%. In ceramics, it's used maximum 25%, and in agriculture, it's used about 20%. And these are the usage of boron in glass. The area which boron products consumes mostly is glass sector, and its function in glass production is to increase fluidity of melted glass, intermediate products, and surface hardness and durability of the end product. Boron is especially used in borosilicate glass, textile type, and insulation type fiberglass in the glass industry. And the consumed boron product is borax pentahydride, boric acid, colemanite, and calcined tincal. And the next slide will come. Yes, boron usage in agriculture. The main aim for usage of boron is as a fertilizer, microfertilizer, herbicide, pesticide, and wood protection. And consumed boron products is borax pentahydride, borax decahydride, disodium octoboride, tetrahydride. Its function is to increase the flowering, the fertilization, and the fruitfulness of the plant, to make the plant more resistant against the match, to increase yield and quality of the plants, and the used products etitot 67, upcol 3367, etikadot, and eticol 43. And also boron used as a cleaning agent, and it is a new area for Etimadan. Boron compounds are a natural cleaning agent. Their function is to facilitate stain removal and bleaching, to stabilize enzymes, alkali buffering, and water softening, to improve the performance of material used as surfactants. Boron detergent used in laundry detergents, household or industrial type cleaners, and personal hygiene products. And here we have boron cleaning products and Borel. And the next slide. Here is the boron used in energy sector. Boron is a hydrogen carrier as sodium borohydride and ammonium boron. They use in nuclear applications like as a neutron absorbent and storage of nuclear waste. Magnesium borate is a superconductive and they transfer the energy without loss, and niobium ferrobor magnets is used in industry. Boron decrease in carbon release in cement and ceramics production. Also boron usage save the energy in cement, ceramics, glass and wool and metallurgy sector. And in this area, borax pentahydride, boric acid, sodium borohydride is used. Here is some usage of boron in ceramics. Ceramic sector is the oldest and second largest market for boron. Boron mainly used in ceramics, glazes, and porcelain enamels to reduce glass fluidity and surface tension, to make ceramics more resistant to physical impacts and chemical effects. And in this area, boric acid, ethyl ceramic, and colemanite and ulexite is used. Also, boron is used in steel, iron and steel industry. Its function is to form slag, to accelerate melting agent in non-ferrous metal industry, and to increase the hardness and durability of steel. And in this area, ferroboron is used in the production of cast iron, permanent magnets, and amorphous metals. Boronizing increases the hardness of steel surface, and boronite light is widely used in surface coating due to its effect and reducing the friction coefficient. And in this sector, borax pentahydride and ground colemanite is used. Here, boron also used in defense industry. Usage area is space and aviation industry, fuel cells, rocket cells, military and armored material and vehicles. Its function is to control the system of atomic reactors, cooling pools and reactors alarm closing, and as a magnet and composite. Consumed boron product is boron nitride, boron carbide, titanium diboride, sodium borohydride, and elemental boron. And Etimaden has started a boron carbide investment in Turkey. This is the first in Turkey. An investment amount is about 70 million US dollar. It will employ 250 people. The production capacity will be about 1,350 tons per year. And the construction period estimated is 24 months. And it will contribute to economy about 25-30 million US dollar. Boron carbide will make a great contribution to the defense industry. Here is some more information about the boron carbide. The groundbreaking ceremony of Balıkesir Bandırma plant, which will produce boron carbide in FEPA and other international science standards, was held on 25 October 2019, and it will be in operation in the next years. And the boron carbide used as a military purpose armor materials, wear resistance machine parts and ceramic materials, neutron holder in nuclear applications, abrasive for polishing surfaces, antioxidant in the production of carbon-containing fibers. Here is boron nitride, another compound used in defense industry. It's formed by boron and nitrogen elements with a chemical formula Bn produced by chemical methods. Its function is prevent corrosion and chemical reaction of the material. Therefore, it is used for coating of the surface of the molds. Also, it is used as a dielectric material in the electronics and electrotechnical industry, cosmetic and ceramic industry, and as a lubricant at high temperatures. And this is a new area for the rare earth, for etimaden. This is a strategical move for the etimaden. The most important known reserve of rare earth deposit of Turkey is the baznezite, fluorite, and baryt deposit located at Kızılcören village of Sivrihisar district near to Eskişehir province. And etimaden commences studies in accordance with the national know-how policies of our ministry for the improvement of this deposit for our country's economy. And studies are carried out in 4 stages. First, in 2011, drilling studies were commenced for the identification of the reserve, and approximately more than 1,100 meters of drilling is made until now. And etimaden and MTA, General Directors of Mineral Research and Exploration, carried out some studies by receiving consultancy from universities in order to gain each mineral at high purities from the complex ore and in order to determine their production processes. Now we are in the stage of building a pilot plant. Project is commencing and the investment process is being continued. And following the project studies are completed, the production plant will be built at site. And rare earth elements have wide usage area. The main usage area are high technology and renewable energy sources. In this context, magnets, catalysts, metal alloys, polygers, glazes, phosphorus, and ceramics are the most important usage areas. Okay, this is the end of my presentation. Thank you for your listening.
Okay, thank you for your presentation, Mr. Tozar. We finished the last presentation of our session, but we have 3 presentations which are not presented yet. We are waiting because the one of them is started at 5 p.m. Thank you for your attendance, Mr. Küçüktürk and Abdel Molla. Now they are in.
And also, thank you.
Thank you. I am waiting them. And now I stop with my video, but the session is opening. The session is open. The session open. And thank you for your attendance again.
Thank you very much for your.
If you want, you are waiting with me, but his presentation start at 5 p.m. It's very long time. Now is 3:30 p.m. Okay, again, I want to thank you for your attendance and for your presentations and for your studies. If you leave, we will.
Okay, thank you for your contribution, for everything. It was good section for us. It was fruitful. Topics will be held in your section. Because of that, I am happy that these organizations was very fruitful for all audience, I think. Thank you very much for everything.
Thank you. I hope to see you at another conference.
See you.
Thank you.
Bye-bye.
Bye-bye. Bye-bye.